Okay. So the outlines of today's presentation is I will commence with a brief overview of data palm trees. Then we will explore the limitations and shortcomings of traditional machine learning, discuss recent development in tree crown delineation, and delved into our research methods and findings. So the date palm tree is one of the most cultivated fruit trees since prehistoric time. It holds an immense economic, cultural, nutritional, and environmental benefits. In 2021, the Food and Agriculture Organization estimated the overall production of dates to be over 90 million tons. And as you can see in this statistics on the left here, the United Arab Emirates is among the top 10 producing countries, and there are about 40 million trees distributed across the United Arab Emirates. So these trees are not only an integral part of the UAE's culture and heritage, but also serve as a crucial agricultural asset. Thus, accurate information about the number distribution of date palm trees is essential for their monitoring, health assessment, irrigation, and sustainable management of the data industry. So continuous large-scale date palm tree mapping from traditional field-based techniques can be challenging, considering that date palm trees are distributed over large areas. And remote sensing provide a cost and effective mean to monitor vegetation in generally and date palm trees. In the past few years, the development of affordable drones and smaller sensing technologies like UAV, LiDAR, and others have greatly boosted the progress of diverse precision farming applications. And they are widely used nowadays in forestry, in tree detection mapping, crop monitoring, crop yield estimation, tree stress detection, and other applications. So with the growing volume of remotely sensed data, a diverse array of machine learning techniques have been developed and employed to pre-process, analyze, and extract meaning of information from remotely sensed data. And these algorithms are trained or are utilized in supervised and unsupervised manners. So they are used in different regression, classification, dimensionality reduction, image enhancement by sharpening, noise reduction, and other applications. So in the context of date palm trees, classical machine learning techniques based on object-based and pixel-based classification are used to map date palm trees. These techniques involve, let's say, for example, object-based involve image segmentation, the extraction of features manually, like spectral indices, NDVI, and other indices, geometrical features, and more features, and the employment of classification techniques like random forest, support vector machine, and of course the accuracy assessment. So these techniques are nowadays known as case specific in nature, that vary from one person to another or from case to another, and they have limited generalization capabilities. So in recent years, deep learning as a subfield of machine learning has demonstrated remarkable capabilities and achieved outstanding success in various remote sensing and geoscience. So in contrast to classical machine learning, where features are manually engineered, deep learning techniques deep learning is data driven, and where high level deep features are automatically learned from the input data set. So generally, the design component and the task of deep learning can differ from based on the nature of the problem and the characteristics of data. In remote sensing, generally, there are various deep learning models are used in the literature, including convolutional neural networks, recurrent neural networks, autoencoders, deep belief network, transformers, and other models. So in the convolutional neural networks, which is one of the most widely used technique, where high level deep features and complex pattern are automatically learned by the CNN from the input data set through learnable layered convolutions. Okay, so convolutional neural networks are widely used in analyzing UAV data in various tasks in recognition, extraction, classification, and mapping of vegetation, agriculture, forestry species, urban tree canopies, tree crowns, and other different applications. And they are used to perform four main vision tasks, including patch-based classification, object detection, semantic, and instance segmentation. So the first task that CNN is used to is patch-based classification, where the input image or satellite or UAV images are divided into small tiles, depending on the size of the object of interest. And these tiles are passed to a convolutional neural network like VGG, ResNet, MobileNet, AlexNet, and others. And they are used, each tile, of course, will represent a single class. And the existence and absence of a particular class in the probability is produced. So, however, this technique may cause fragmentation or misclassification if the object of interest is smaller or larger than the image size. Okay. So the second task is semantic segmentation, which is nothing but it refers to pixel classification, per pixel classification, where each pixel from the input imagery is assigned to a specific class. Like here we have image, and each pixel that corresponds to palm trees is highlighted. The third task of convolutional neural network is object detection, which refers to the identification and localization of object of interest by a bounding box or rectangular box. So the last one is instance segmentation, which is are hybrid techniques that combines object detection and semantic segmentation, which concurrently localize the object and perform pixel classification for object instances. So generally, the increasing availability of UAV images with different heights, different spatial resolution, of course, the remote sense data can be acquired by different platforms, different UAVs, different aerial images, satellite images, and so on. So the high intra-class variance, we have different kind of dead palm trees that vary in terms of age, size, height, overlapping crowns, and so on. We have also different complexity of different image background, image context, and backgrounds. You know, dead palm trees can exist in agricultural and urban landscapes. All these make the accurate and automatic detection of dead palm trees from multi-source and multi-date remote sense data a challenging task. So as I highlighted the utilization of convolutional neural networks in different tasks, but considering that features are extracted in traditional convolutional neural networks within, you know, kernel, what we call local receptive field. So this poses a challenge in effectively capturing the global information. In general, various techniques are used, various technique integrated self-attention mechanism into CNNs to address the limitation and this limitation capture global information. So instead of directly encoding the global context information, these techniques such as pyramid pooling module, dual attention module, and others, they just only aggregate global data by combining locally extracted features. Thus, the utilization of convolutional neural networks in extracting, let's say, dead palm trees in a complex environment and multi-scale images can be challenging using convolutional neural networks. So in the past few years, I think we have all heard about transformers, which is the the success of transformer in natural language process has opened new research avenues in area of computer vision. So the primary driving force behind the development of transformers in natural language processing was to enable parallel processing of word within a sentence, as you can see in this image on the left. So which was not feasible in recurrent neural networks or LSTMs, as you know, neural network and LSTM process words sequentially, one at a time. But vision transformers or vision transformer are perform, you know, they process the data independent of their order and in a parallel manner. So in the computer vision, you know, vision transformer nowadays are performed the same concept. The image is divided into, the input image is divided into small tiles. And these image tiles, let's say 16 by 16 or 32 by 32, this is just an example. These small tiles are treated the same way as tokens or are as words, okay? So these small patches are flattened into one-dimensional sequence or vector. So through linear, how do you call it? Learnable linear projection with dimension E. So the position encoding is, the position is embedded by a positioning embedding with also extra learnable class. So all these patches are independently passed through vision transformer encoder, which consists of multi-head self-attention. So the goal of self-attention is to capture the local and global dependencies and learn the relationship between these image patches. So in broad terms, the self-attention mechanism can be perceived as the attention weight or scores between each batch embedding that are computed to capture their relationship. So as I highlighted, unlike CNNs, the operations here are parallelizable, independent of order, enabling the capture of global and contextual information. So recently, there are a wide spectrum of machine learning techniques have explored, of remote sensing study have explored the utilization of vision transformers. So the main objective of this research is to provide an end-to-end and efficient deep learning framework to detect individual date palm trees from multi-scale or multi-date remote sense data. So first, we examined the reliability and the efficiency of various CNN and transformer-based models. And we developed an automatic framework to detect date palm trees, individual date palm trees from large-scale images. And we attempted to verify and assess the generalizability and transferability of the evaluated instance and segmentation model. So the method, this is the methodology here. We are focusing on two of the main vision tasks, which is instance and semantic segmentation. So generally, this is the overall framework or flowchart. So it starts with data collection. Data was collected from different sources, UAV, aerial images, satellite data, and followed by the data preparation, where the data was prepared for semantic and instance segmentation task. We will discuss the details in the subsequent slides. So in the instance segmentation, we have evaluated different vision transformers. And in the instance segmentation, we attempted to develop a framework to detect and map individual date palm trees. And of course, we eventually evaluated the transferability, generalizability of these models on UAV data and on satellite data. And ultimately, these models were applied to large-scale images. So the study area of this research is located in the United Arab Emirates, in the Ajman Emirate, which covers 30 kilometers square, with in different, which like the study area is characterized by different agricultural and urban landscapes. So this is the method. So on the left side, we can see the UAV data. This is for the first objective. The UAV data on the left side. In the middle, we can see the ground truth data. And on the right side, we can see the multi-source data. So after following the data processing and preparation, the models, different vision transformer models like SIGFormer, upper net swing transformer, segmenter, dense prediction transformers, were applied with different model complexity, were developed on UAV datasets, and were also developed on multiscale datasets, and the generalizability and transferability of these models were investigated. So this is the study area is, the dataset used in this research consists of satellite data, UAV, aerial images. I would like to take this opportunity to express our sincere appreciation to Municipality of Ajman for their continuous support and providing the dataset used in this research. So, of course, having sufficient and sufficient and high quality ground truth data is essential for deep learning models. So we have comprehensive training data from these different data sets. In the UAV data set alone, we have about 50,000 dead palm trees. And in the satellite data, we have like almost 48,000 dead palm trees. So in the data preparation, first of all, this is the data preparation for semantic segmentation. So considering that, remotely sensed data is, very huge, it cannot be fed to deep learning models directly. So the images and the corresponding label, they are divided into small tiles. It could be, in this research, we divided them into 512 by 512 pixels. So for the UAV, each pixel is 5 centimeter in the ground. In this table on the left, we can see that these are the statistics for UAV data and 2 aerial images. So the data set was divided into, training, validation, and testing data set. So on the right side, we can see the image and corresponding label of UAV data set. In the first row, and the second and third row, we can see the UAV and corresponding, the aerial and corresponding mask. Aerial images and corresponding mask. Okay, so as I mentioned, we have employed various vision transformers. These are some of the state-of-the-art techniques, including SIGFormer, swing transformer with the upper net encoder, segmenter, and dense prediction transformer. All these are transformer-based models where the input images are divided into tiles and fed to a set of multi-head self-attention mechanism or different blocks. So they have similar concept, but different architectures, and of course they have different capabilities. Also, these models, the vision transformers, were applied to some of the widely used instance segmentation architectures, including DeepLab version 3+, PSPNet, dual attention networks, and FCN networks. So the evaluation metrics, these models were evaluated by different accuracy metrics. Some of them include the mean intersection over union, which compares like the agreement between the ground truth data and the prediction. So the mean intersection, the value ranges like say from 0 to 1 or 0 to 100. So the higher the value, the higher the agreement between the prediction and the ground truth data. Also, we have utilized the F-score metrics. The generalizability and transferability of deep learning of these models were evaluated first on multiscale UAV dataset, ranging from 10, 15, 20, and 30 centimeter, and also on a public dataset that made public by MOHAMED BARAKAT Space Center, which was acquired in Al Ain city. So this dataset is available in XML format, object detection format, but we have delineated the boundaries of dead palm trees. So these models were trained on MM segmentation framework. It is an open source deep learning framework, like semantic segmentation toolbox. These models were trained on a Linux cluster with 8 NVIDIA Tesla K8 GPU. See, these are some of the hyperparameters. So the models were trained for 50,000 iterations and evaluated every 2,000 iterations, and the batch size was set to fully utilize the 8 GPUs. So, of course, combining satellite and UAV data could lead to more comprehensive and depth assessment of data boundaries, as satellite data, cover large areas in comparison to UAV data. So we attempted to use what we call transfer learning to these models were the instance semantic segmentation models were trained on UAV and aerial images. So these models, the knowledge that gained from training from this data set was transferred to and detect dead palm trees from satellite data. So this was for the first task, which is semantic segmentation. And the second task was, to develop an automatic framework to detect individual dead palm trees. So the method here, I will go swiftly. Following the data preparation, a data conversion framework was developed to convert the data to common object in context instance segmentation annotation format. And mask RCNN based on a swing transformer and feature pyramid network was utilized. The generalizability of the model was evaluated. And we have also utilized and improved a vision library called slicing edit hyperinference to perform inferences on large scale images and convert the result into vector format. So first, considering that the majority of instance segmentation models requires the data to be in COCO annotation format, it's common object in context format. We have utilized this kind of framework. First of all, the vector labels, the digitized in ArcGIS software or in any software for vector data processing. So it's converted into raster format where each tree should have different attribute value, and this raster is processed to extract the contour. So the contour of all pixels have the same attributes. The contour will be extracted and will be saved as a JSON file. So for each image will have different JSON files, and these JSON files are converted into COCO annotation format using label me module, which is also an open source library. So we can see here, these are some of the image tiles and the corresponding labels. Okay. So in terms of the training, the data set was divided into 3 sets. So for the training, a set of 23,000 images were used to train the model, and also 3,500 images. I mean here image tiles were used as a validation to monitor the progress of the model and to optimize the hyperparameters. And also a set of 3,600 images were used as an independent testing data set. After the best model is selected, these data sets are used to evaluate how the model will perform on a new data set. I forgot to mention that this data set, the training data set, was increased 3-fold by artificially, rotating the image, mask pairs by 90, 180, and 27 degrees. So just going swiftly, the architecture is based on mask RCNN, which is a commonly used instance segmentation architecture. But here we have used the swing transformer as a backbone, and with the feature pyramid network. So this is the typical architecture of mask RCNN, which includes the feature maps. These are the feature maps extracted by swing transformers, and the RBN used to propose some of the bounding box and so on. Then goes through ROI line, and ultimately it goes to fully connected layers and fully convolutional layers to produce the the bounding box as well as the segmentation mask. So following the training of the models on the data set that I mentioned, We have employed a line weight vision library for it's called slicing aided hyper inference. UAV images or satellite images are very huge, and the model was trained on 512 by 512 small batches. So it is impossible to load a new image. Let's say you have 5 kilometers by 5 kilometer image and you want to detect dead palm trees. You cannot directly feed the data to the model. So the data has to be divided into tiles, overlap tiles, and we have used this kind of model. So this model is reads geotagged images with the coordinate system using GDAL library, subdivide the image into tiles, read the images as a list, and each one for each image it performs the inferences, and sorry, and it converts the instance segmentation results into vector data to be used in any GIS database. So to evaluate the model, also here we have used a common instance segmentation or object detection metrics such as mean average precision and F-score. For the generalizability, similar to instance semantic segmentation models, we have evaluated the generalizability and transferability of the model into multiscale and independent testing data set. We have also compared the performance of the model with the various CNN-based models based on residual learning networks, ResNet 50 and ResNet 101, including different mask RCNN architectures, point rendering, you look at coefficient and other models. And so for the experimental settings, we have employed, these models were trained on two main libraries, vision libraries known as detection and Detectron-2, which is developed by Meta AI Research Center. So this algorithm was trained on a local system with RTX, Titan RTX graphic card with 24 gigabytes. And they were trained for 100,000 iterations. And of course, we have utilized ImageNet pre-trained weights. So now let's jump to the results and discussion. So in the result, we will start with the result of semantic segmentation, and then we will go to the instance segmentation and draw some conclusions. So first, as I highlighted earlier, the model was trained on UAV dataset first, right, to detect dead palm trees using different vision transformers. So this, a graph here on the left shows that the model, the evaluated model, successfully delineated dead palm trees with the mean intersection over union ranging from 85 to 86%, and F-score ranging from 91.6 to 92.4. So in this figure on the right, it shows, starting from the left, it shows the sample of images selected from the testing dataset, the image ground truth label, as well as the followed by the segmentation results of dense prediction transformer, and in the end here we have SIG-Farmer model. So the result is impressive, actually. Second, the model was developed also on multi-scale dataset on UAV plus 2 aerial images, 5 centimeter UAV data, 15 and 20 centimeter ground space distance dataset as well. So on the left side here, this analysis showed that the segmenter model was the least accurate, and while the generic SIG-Farmer and AberNet spin transformer could map dead palm trees with an F-score of 92% and mean intersection over union of 85%. So we can see here in the image here, we can see the result of detection of dead palm trees from different data set, which is sometimes it's really challenging to visually differentiate between different trees on RGB images on like 20 or 30 centimeter accuracy, but the model was very efficient in detecting this dead palm trees. So in terms of the generalizability, it's very essential to know the capabilities of the model. Of course, as the spatial resolution of the data decreases, of course the accuracy will decline as well. So here in this, on the left side, we can see the ground. On the x-axis, we can see the spatial resolution of the data when we have different 55 to 30 centimeter, and on the y-axis we have different architectures. So we can see that when the model, all the models maintain almost similar accuracy when applied to 10 centimeters when the 10 centimeter images. However, the accuracy was, the accuracy decreased by 11 to 23% when applied to a data set with a spatial resolution of 20 centimeter. Okay, in terms of the transferability, as I mentioned, the model was applied to data set in Al Ain City. So the UAV and generic multiscale, the model trained on UAV data set and trained on how do you call it, multiscale data set, like produce similar range of accuracies, which prove the capabilities of the vision transformer to capture global information, produce meaningful results. So when it comes to comparing between vision transformers and convolutional neural networks, the accuracy is not only used to evaluate between these models, but we have to consider the model parameters, the computational cost, the training and inference time, of course. So, of course, the sigformer and upper net spin transformer produced high accuracy in both multiscale UAV dataset and also independent datasets. In terms of the model parameters, the segmenter was has the least number of parameters, but however, it was also it produced poor results. So the sigformer showed it was the sigformer and upper net based on spin transformers produced the highest result. And the sigformer model was the lowest number of parameters and lowest computational cost and least amount of training and inference time. We can see this image shows the result of innocent segmentation on different image tiles on large data set. So in the end, we want to create a database for data palm trees from multi-date data. So the model was, multiscale model was, this is the result of sigformer model, was able to accurately delineate date palm trees from different data sets. So as I said, we have used here sigformer model, and we utilized like if we use multiscale data set to directly detect date palm trees from satellite data. This is the WorldView 3 satellite data set with 30 centimeter spatial resolution. So we can see, the models delineated to some extent date palm trees, even did not see this data with different kind of data set, thanks to the representational power of transformers. But fine-tuning the model on additional satellite data set, we were able to improve the accuracy by 70%. So this analysis showed that date palm trees could be mapped from WorldView 3 satellite data by F-score of F-score of 85% and mean intersection of reunion of 77%. Sorry. So in terms of the instance segmentation, I'm running out of time, so I will try to go swiftly here. So for the instance segmentation, this is the proposed method, which was based on swing transformer, feature pyramid network, and slicing aided hyper inference model. Sorry. So the evaluated instance segmentation model, the proposed model, showed that date palm trees could be segmented with the mean intersection of reunion with mean average precision of 91.5 an F score of 94%, which we can see here. Date palm trees were delineated very well. So the generalizability also showed that, when the models applied to 10 centimeter accuracy, the transformer-based models maintain similar range of accuracies. And both of the, transformer-based model based on swing transformer, swing tiny and swing small also produce promising results. The transformer-based model also had limited hour of training time and high inference time, and it shows the capability of to detect dead palm trees from different spatial resolutions. So the overall the superiority of swing transformer can be attributed to the high representational power of of the transformer-based model to capture global information. For instance, you can see here figure A and figure B. It shows these are the feature maps, some of the feature maps extracted by ResNet, which is a CNN-based model, and a swing transformer-based model, and it shows that the capability of a swing transformer to capture, to perform self-attention mechanism on small images and shift and compute the self-attention mechanism on different, it shifts windows and it gradually enlarges the receptive field. It results in, high representational power. We have also obtained a high accuracy on independent testing dataset. So lastly, so after the model is trained on the instance segmentation here, we have used the UAV dataset. So in order to apply the model on a large dataset, we utilized, SAHI approach with dividing the image into 512 by 512 with 30% overlap and confidence threshold of 0.4. We have also applied non-maximum suppression to refine the result. So we can see here, this is the result of like 500 meter by 500 meter, like almost square kilometer. And we can see here the result in the comparison between the ground truth data and the result of deep learning model, which is a remarkable result. So in conclusion, in this research, we have attempted to evaluate different vision transformers and propose an instance segmentation framework to detect individual dead palm trees. And so, the vision transformers for semantic segmentation showed promising results with a mean intersection of reunion ranging from 85 to 86% and F-score ranging from 91 to 92%. The sigformer model and followed by ARPANET based on a swing transformer outperformed all of the evaluated CNN-based models. And the sigformer model was not only, produce efficient results, but was also, it has few number of parameters and low computational cost. So in terms of the instance segmentation, the model could, the proposed model could delineate individual dead palm trees with a mean intersection of reunion of 92%, 91% for the segmentation, and F-score of 94%. So overall, the instance segmentation, the proposed instance segmentation framework could be used to, establish dead palm tree inventories, update existing geodatabase, automatically detect, count, delineate dead palm trees from large-scale UAV images. So these are some of the published work. For more information, you may refer to this published work. Some of the findings of this research are published in Drones, Geocartoon International, and Remote Sensing Journal. So this is the end of my presentation. But on behalf of Professor Rami, I will just take before the Q&A session, I will just take a few minutes to discuss about our master program in the University of Sharjah.